The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
The next talk is by Raissa Ferron from University of Texas at Austin, and she's going to talk on approaches to producing additively manufactured.
Good morning, everyone. My name is Raissa Ferron. I'm a faculty member at the University of Texas at Austin. And today I'm going to be talking about approaches to producing 3D printed materials. And this presentation is actually going to take a step back and actually really talk about ways to produce 3D printed materials and the reason why we want to do this. So as we know, there's been much advancement in concrete technology that has enabled us to really push the envelope in terms of ultra-high performance concrete mixtures. And we've really seen advancements in terms of like high strength, the flowability of the mixtures, durability. We're also seeing a lot of work being done in terms of really trying to control the modulus of concrete. And this has enabled us to have, structures such as you see here with the Burj Khalifa. But when we actually take a step back and really think about how do we produce concrete mixtures, we really see that the process for manufacturing concrete has remained unchanged for a really long time. Over here, these are pictures showing how concrete was mixed on site in the 1950s, and you can see that if you're hand mixing concrete in 2017, 2018, it's basically done the same way. And if you say, well, we actually do ready-mix concrete, so you should be showing ready-mix concrete because that's about 70% of the concrete production in the United States. Over here, I show a picture showing ready-mix concrete being placed in the early 1950s, and almost 70 years later, almost, a century later, we're basically still producing concrete the same way. So we see that this process for manufacturing concrete has remained largely unchanged. But one of the reasons why we're all here today is because it's the fact that with digital fabrication of concrete mixtures, this may actually change the game. So it's a transformative process that really can change the way that we are producing concrete mixtures. So digital fabrication is essentially this application in which you're using digital modeling coupled with some type of automatic robotic technique to produce concrete mixtures. And the general steps consist of having some type of 3D model of the desired objects, and there's various software programs that you can use. The next step would be to actually take that model and to convert it into a STL file. So in this sense, your model is now going to be represented in a series of 2D layers, and then this design can actually then be transferred to the printer so that it's readable. You can actually skip that step, but it makes it a little bit more efficient. But the real goal here is actually for you to get a G code. And again, this G code is going to be this program that's going to tell the printer what to do. It's going to tell the printer how far to move to the left, how far to move vertically. And then with that said, once you have your G code, and of course you need to have some type of printer, you'll then be able to export that file over to the printer, and then your printer can print the material. So one of the reasons why we're really excited about additive manufacturing, and not just in the concrete community, but throughout the world, is because with the use of additive manufacturing techniques, this is really one way that you can produce mass customizable materials. So we have people saying that this is actually like the third industrial revolution, because we know how to mass produce cars and other type of elements. But really when you talk about customizing elements, it takes a lot more time. So the true advantage of additive manufacturing is that it's going to be able to allow you a way to mass produce elements, but still be able to do it quickly and efficiently when you want to customize certain aspects. So there's two major types of digital fabrication techniques. There's additive manufacturing, which is typically what we tend to use in concrete technology, but there's also subtractive manufacturing. I'm not going to talk about subtractive manufacturing because, again, we really see that most of the work is focused on additive manufacturing. The most common type of additive manufacturing technique that is used, and you've seen it, I think, in just about everybody's presentation, is this layered extrusion-based approach in which you have your mixture and you're essentially just casting it layer by layer, and over time your cementitious material is going to develop structure of a building, its yield stress is going to increase, and that's going to allow it to be able to carry additional layers. So there was just a great question regarding whether we can use technologies that's happened in the paving communities in terms of slip-form pavements and utilize that with regards to additive manufacturing. And the answer is yes. I think that provides a really good basis in terms of really understanding how we can make these shape-stable materials that are still able to flow. But when you look at slip-form paving materials and you look at 3D printed materials, the key difference is regards to the height. With the slip-form paving materials, you're not really looking to carry as much layers as you would what we're talking about trying to do here with regards to 3D printing. So again, this 3D layered approach is really what we see being used throughout many regions of the world. And about a year ago, a company named Icon printed a 3D printed house in Texas, and again, they used this layered 3D printed approach. Essentially, there was a lot of publicity regarding this printed structure. But in addition to this layered 3D printed approach, there's other types of additive manufacturing techniques. You have binder jetting, which is actually produced by using cement or liquid, and you essentially are going to be injecting the liquid, and then you're going to have a reaction that will solidify the particles with whatever liquid you are injecting into the system. And this could actually be a really good approach when you're looking at trying to produce vertical curved elements, such as arches, because you have that powdered bed in there that's actually going to provide shape stability. There's also slip forming, which we're seeing at like ETH Zurich, in which you're essentially, it's a little bit more like slip form paving, in which you have your formwork and you're just vertically moving it up. With regards to 3D printing systems, there's two major types that we see. One is a gantry printing system, in which you have a platform, and essentially you're moving your printer head in orthogonal arrangement. The major, I would say, constraint with regards to this type of printer is the fact that your printing frame should actually be at least as large as the dimension that you're trying to print. And then we have these robotic arm printers. The advantage of the robotic arm printer is that you can have free-form printing. You have much more degrees of freedom. They're relatively more easier to install. Some of the challenges with regards to robotic arm printers are that they're more expensive than the gantry system. In addition, there's sometimes concerns about safety measures with regards to the robotic arm, because it's very easy for the robotic arm to perhaps swing out of place. So you want to make sure you have some additional safety measures, such as the cage installed. And this bottom picture here is a picture of the robotic arm printer that we have built, I can say have built now, not are building, at UT Austin. So over the last 2 years, we've really seen this explosion with regards to large-scale 3D printers. And there's several desktop 3D printers, but again, if we're talking about construction applications, we want to be able to scale it up. So over here, this is just a table showing a couple of the 3D printers that we found on the market. There's a couple of things that you can notice. One is that for these printers, that is going to cost an investment of around $250,000 at the low end in order to have one of these printers. Two is that we can see that all of these methods are using that layered extrusion-based approach. So we're not seeing binder jetting or slip forming. So there's also, potential in those two types of techniques. And then three is that we can see that the majority of these printers are actually this gantry type approach and not the robotic arm. But regardless of which type of printer you're going to use, I would say there's essentially two approaches to producing these materials. One is going to be this stiff, like extrusion-based approach in which you're just using high pressure to ram the material through the printer. I would say this is more similar to the approach that the Army Corps of Engineers have been using to produce their barracks. And then the second type of approach is what I'm calling the more flowable approach. And I believe this is more in line with the majority of the presentations here, in which you have a mixture that is flowable enough to be extruded out, but then develop really quick shape stability. Regardless of which approach you're using, you're going to be concerned about various fresh state parameters such as the extrudability, the buildability, the pumpability, and of course the scalability. So essentially what we're talking about is that you're going to be concerned about the flow and deformation behavior of the material, so the rheology of the material. At UT Austin, we're taking a multi-scale approach to tackling this problem. We have a benchtop printer that we are building from scratch. It's about 3 feet by 4 feet by 3 feet high. And I have included some of the software programs that we're going to be using in order to develop that. And then we also have a large-scale printer that we have built, and this is a robotic arm printer. And you can see over here a picture of one of our first prints. The nozzle itself was also 3D printed, so we're really excited that now we're able to print. And again, this is large-scale. The arm has a reach of around 6 feet or so. And essentially what we're doing is that we're trying to understand fundamentally how do you scale up from like the desktop type of mixtures all the way up to a large scale concrete mixtures. And in particular, we're trying to figure out, like many others have stated before, what are the rheological parameters that's going to impact the performance of these mixtures. So you can see over here that we have a figure which is showing the yield stress versus the viscosity. See, the yield stress versus the viscosity of the mixtures. And we can see that when the viscosity is too high, that you definitely have mixtures that are going to fail. We can see that in this zone over here that all of our mixtures are passing. But what's really interesting for us is trying to have a better understanding about what's going on in this region over here. This region in which you have mixtures that have similar initial rheological properties, but you have some mixtures that are passing and some mixtures that are failing. We're looking at various different mixture compositions. And one of the initial aspects that we're seeing is that in addition to the initial rheological properties, another factor that plays a big role is going to be what we're calling the cohesion of the mixtures. So rheological testing is great in order to tell you the initial flow and deformation behavior of your materials. But when you're thinking about 3D printing and you're extruding something through, when you're using shear rheology testing, they're not necessarily the best techniques in order to capture how the interface between the solid phase and the liquid phase is going to perform. So what we're seeing in some of these mixtures over here is that even though they have similar rheological properties, that when you're extruding out the materials, you'll get some of the water essentially being squeezed out. So the cohesion of the mixture is also something that we need to pay attention to. So just to summarize, we see that there's different approaches to 3D printing concrete materials. The layered extrusion approach is the most common. We also know that large-scale digital fabrication of concrete is possible and feasible. I showed a picture from Icon. There's Winsun, there's Contour Crafting, who's all shown that it's able to be done. And through this method, you're able to have quicker construction, less labor, less overall costs, and also utilize less materials. And again, this is really exciting because this allows us a way to mass produce customizable concrete elements. And truly, in order to really advance this, we need to have a better understanding of the properties and performance of additively manufactured materials, both from the fresh state as well from the hardened state. And there's also work that needs to be done in terms of like slicing technologies, ways that we can incorporate building information system modeling into this technique. So with that said, I would like to say thank you for your time and attention. And this picture over here is actually a concrete printed chair that I sat on when I was in Thailand that was produced by SCG Group. Thank you.